Hi Level 2s and welcome to 2.5 Organic Chemistry. This is Lesson 4. Our learning objectives for today is to define structural isomers, to draw structural isomers, and describe how the physical properties of these isomers are in fact different. Okay, so what is a structural or constitutional isomer? I don't tend to use this name here. Both will be provided in the exam, but more commonly than anything is the term structural isomer. So what is the definition of a structural isomer? It is that they have the same molecular formula, okay, but their atoms are arranged differently. This definition is an essential one to know, so you need to make sure you've got that definition sorted. It's required in many of your answers to get excellence. So what does this mean? So if you have this molecular formula, C4H10, and remember a molecular formula tells you the type of atoms present and the number of those atoms present. So in this structure there are 4 carbons and 10 hydrogens. Well, this here, we could actually represent this in 2 different ways. It can either be butane, because that's got C4 and 10 H's, or it could be 2-methyl propane, because that's got 4 carbons and 10 hydrogens. And so these are called structural isomers because they have the same molecular formula, but they have different structures. And the key thing about structural isomers is that they always produce different names. Okay, so they always produce different names. So if you're able to draw 2 structures with this, or more, because there will be more, with the same molecular formula and they produce different names, then they're said to be structural isomers. Now there is a bit of a systematic way of doing these, so it makes it a lot easier, and I'm going to talk you through those. Okay, before we do, I just wanted to mention to you that structural isomers have got different physical properties. Okay, and their chemical properties are relatively the same. And the reason why their chemical properties are relatively the same is because they're made up of the same atoms, so they have the same functional groups. But the physical properties will be different because all of our organic substances are organic molecules. And you guys will remember, because we've done an entire topic on 2.4 about how the structure of a substance affects their physical properties. And so the same goes here. Okay, so for instance, we learnt about intermolecular forces and about how if you had a larger shape, then the intermolecular forces would be, or a larger molecule, the intermolecular forces would be stronger, and the same goes here. So we'll talk you through them as we go forwards, but what are some of the physical properties? We're talking things like melting point, boiling point, so that's referring to strength of intermolecular forces, and if they will dissolve in water. Do you remember that's to do with if the molecule's non-polar, it won't dissolve in water, and if it's polar it will. So all of this hopefully is coming back, and density. So this is kind of a nice link into a topic that you've previously covered about physical properties being like your melting point, boiling point, solubility, and how it links to their structures. Chemical properties, when we talk about this topic, are all about how those substances will react with reagents. So just here's a wee note in the example that we were talking about. So the 2-methyl propane and the butane. So here's butane here, and here's 2-methyl propane. So this is a straight chain, okay, and this is a branched chain molecule, and that makes a big difference to the physical properties of these substances. We've previously covered this, but just to recap, a straight chain molecule is able to line up next to each other more closely, which means there's a greater surface area between the molecules. And when that happens, the strength of the intermolecular forces is stronger, and that means that the boiling point is higher because it's going to take more energy to break the intermolecular forces. So if you look at the boiling point here, it's -0.5 for butane, whereas so this branch chain one, it creates more, you can see at the top here, more of a circular shape compared to this one. So they don't pack together as closely, because if you try and pack circles together, there's a lot of wasted space. There's only a few points where they actually make contact, and so therefore the intermolecular forces are actually weaker, and so therefore less energy is required to break them. And that's why this one's got a lower boiling point of -10, because the intermolecular forces are weaker. And you can see that here. So it's to do with the shape. So if you have a branched chain isomer, they will always have a lower boiling point compared to a straight chain, and that's purely because the straight chain can pack together more tightly, and it means there's more surface area between the molecules for those intermolecular forces to form, so more surface area. Cool. Okay, so how do we find structural isomers? So there is a technique here. Okay, and so the task that I'm setting is to work out how many structural isomers there are with the formula C5H12. Okay, C5H12. The best piece of advice is to first of all start drawing the longest chain first. So if we were to draw the longest chain of C5H12, I would just put 5 carbons all in a row and then add in the hydrogens. Now please note, if you don't include your hydrogens, you will not get a full mark in chemistry. So you must have the hydrogens. Don't be lazy, just get on with it. Okay, so there are 12 hydrogens there. That's the first isomer. So that's number 1, straight chain. So once we've done that, what we can actually do is now make that parent chain shorter by creating a branch. So that's what we're going to do here. So 1, 2, 3, 4. So now I've got 4 carbons in my parent chain. Now if you remember back to our naming, which we've already spent quite a few lessons on, we know that you can't put a branch on this end carbon, because if you did, then it would still be the same as above, because it can read round corners, which means that the branch chain has to go on carbon 2 or 3, but we know regardless of which one we put it on, because you always give the branch the lowest possible number, there's actually only one option here, and that's putting it on carbon 2. Okay, so we've done that now. Now before we move on, we're actually going to go back and name these 2 structures that we've named, because one of the things you can do is to check you're actually correct. They should produce a different name, and if they don't produce a different name, then you've actually drawn the same thing twice, and that often happens when you're working out isomers. So this first one is just 5 in a row, so this is pentane. The second one is 2-methyl butane. So we would normally at this point at step 2 try and see if we could place that branch anywhere else on the chain to see if it produces a different name, but we know we can't, because if we put it on this 3rd carbon, remember, then the name would actually still be 2-methyl butane, because it would just read from the other side. So the next technique is to now remove another C from the parent chain, which would now make our parent chain 3. Now if our parent chain is 3, we only have one option to place the other 2 carbons, because we can't put both down this middle one. We can't put both off the same carbon going down, because that would mean that we've still got 2-methyl butane as above. So instead we have to separate them out and put one above and one below. And if we put in all our hydrogens, because you can't forget your hydrogens or else you'll lose marks, we can now actually see what this would be called to check that it's got a different name. And if we were to name this, this would be 2,2 dimethyl propane, another name. And that means that we've actually created the 3rd isomer. So now what we can actually look at is, could we decrease that chain anymore? And the answer is no, because there's no way we could put all the remaining carbons on. So there's actually 3 isomers of C5H12. There's pentane, 2-methyl butane, and 2,2-dimethyl propane. Now these take a bit of practice, and that's what we're going to do all lesson. And here are the 3 isomers, and we just work them out. So if we do the isomers of hexane together, I'm going to talk you through this. I know that they're drawn up here for you, but just to go through it together, to get a picture of how these work. Now, as if you actually looked at those instructions I had on this slide here, I actually say not to worry about the hydrogens till the end. It's up to you whether you do that. You've just got to remember to put them in. So let's do the first one. We always start with the longest chain. So 1, 2, 3, 4, 5, 6. So here's 6. I'm going to leave the hydrogens just to show you how you can do the skeletal method, and then you can plug the hydrogens back in again. Okay, so hexane, the isomers of hexane. Hexane has the formula C6H14, and I know that because this is an alkane, and so I know the general formula of an alkane is CnH2n plus 2. Okay, so it's an alkane. So there's the first one, 6, and that's hexane. So we've done the longest chain, so the next technique is to decrease that chain length. So I'm going to make it have 5 carbons, and so now I need to move where that branch goes. So the first one, I always am systematic, I just put it 1 in from the end. Okay, so by doing this here, I've now made 2-methyl pentane. 2-methyl pentane. I always write the names just to make sure I don't make a mistake. So now what's cool about this one is we can actually move that branch further along this 5 chain and it will still produce another name, because if I put this carbon on this middle carbon, then it's going to be 3-methylpentane. And so that's what I'm going to do here. 1, 2, 3, 4, 5, and this one's going to be 3-methyl. So it's really important to name as you go through to make sure that you're correct. Now, could I move this carbon to this one here? And the answer is no, because it reads forwards and backwards, so that would be the same as 2-methylpentane. So I'm actually done with my 5-chain carbon chain parent chain. So now I'm going to change it to 4. 1, 2, 3, 4. Now you've got to be careful with 4 about where you put your branches, because we've got 2 branches to put now, because we've got 6 carbons. They can't go on the 2 end carbons, because that would mean that you had you were still making a larger chain molecule. So they have to go into these middle ones. And so how could we do that? Well, if we put 1 here and 1 here, okay, would this give a different name? And so you've got to check that the chain length is still going to be short, and it will. So if you put 1 here and 1 here, okay, you still have butane being the largest structure, okay? And so actually this is the one I'm doing here. They've drawn this one really weird. That's just not how I draw it. This is how I draw it. So you can see here you've got 2 branches, and this one would be 2, 3 dimethyl propane. 2,3-dimethylpropane. Okay, so then we can still see if we can do another one with 4 carbons, and if we've got 4 carbons, we've put them on 2 different ones. So what about if we put them on the same one? And if we put them on the same one, it doesn't matter if we put them on this carbon here or the one next to it, because it reads forwards and backwards. So this would be 2,2-dimethylbutane. And you can see there's no way we could decrease the chain length to 3 and fit 3 carbons on it, because carbon can only hold 4 bonds. And so we've actually done all of our isomers. Okay, so the way this one's drawn here in this imagery I think is confusing. I think this one that I've done makes more sense. But you can see these are the isomers. They've all got different names, and there's a systematic way of doing it. Okay, I would then have to go back and put all my hydrogens on these, but I think you guys get the kind of gist of this. So here's a bit of a hefty task. So this task is to draw all the isomers of heptane. Okay, so I'm going to pause this video here, and I'll start the next one to go through the answers, because I'm going to run out of time here. So give this a go on your own, be systematic about it, and I've given you a big hint that there are 9. So we'll go through this in 2 seconds. All right team, see you soon for part B.